Hi y'all, back for another round of physics, and hey, let's get at it. So I'm going to run some example problems today, and one of the first things I thought I would do is let me show you that you can indeed solve a problem sometimes with forces or with energy. So I want to give you an example of that where we'll run through a box on a ramp problem using forces, and then we'll turn around and do it with energy, and we'll see that we get the same result. Okay. So that's the first one, and then we'll just start running some additional example problems after that. So here's what I have for you. Box is released and slides down a frictionless ramp. So notice frictionless ramp from a height h. What is the speed of the box at the bottom of the ramp? And so again, notice we're doing friction. Okay, so that's always nice. Frictionless, excuse me. Frictionless, we have a height. Okay, so go ahead. We should probably sit down and we should draw a picture of this situation. Got it? Well, bam. Greg prepared early. So there we go. We've got a box, and actually I'll go ahead. I'll label this theta. So we'll label that theta, and we're told that it starts from a height of h above the surface. So we have h. Okay. I should probably draw in some axes here, so we'll go ahead and do that. Let's get y-axis perpendicular to the ramp. We'll do an x-axis parallel to the ramp going down. So we'll go ahead and call that y and x. So here's y, here is x. Well, if we're dealing with forces, so we're specifying right now we want to do this with forces, well, we better do a free body diagram. So system, we will take to be the box, and our surroundings, we've got the ramp, we have our normal force, okay. And we have the earth, which is our gravitational force. Okay. And free body diagram. Best drawing ever. There's my box. Normal force is something like in this direction. Call it Fn. And our gravitational force is somewhere in this direction. We'll call that Fg. Fg. Keeping in mind, of course, that this is still angle theta. Good? Cool. Well, now, since we're specified that we're doing forces, we better write down our general equation, and our underlying physical concept is Newton's second law. So we have F net equals our mass times our acceleration. So we have that. And specifically for this case, we're going to look for which direction? The x component. So we're going to look at the x direction. That's the thing that I care about, the speed at the bottom of the ramp. That will be the speed in the x direction. So x direction, and we'll go ahead. We have F net in the x direction is equal to ma x. Okay. Well, looking at the forces in the x direction, we notice that the only one is the component of gravity parallel to the surface of the ramp. So we have the gravitational component parallel to the surface. That will be equal to ma in the x direction. Let's go ahead and substitute in our definition now. Gravitational force, the magnitude's mg. We see that that component's in the positive x direction, so we're okay there. And we take the sine of the angle. Sine of theta equals max. Oh, goody goody. The masses cancel. And so we have an acceleration down the ramp, which you already know, g sine of theta equals the acceleration down the ramp. Well, now that I've got that, now that I've got the acceleration down the ramp, how am I going to get the speed of the box? We can go to the kinematic equations. Okay, constant force. That means that my acceleration is constant. That means now I can apply kinematics. So we actually have a two-step problem. The first step, find the acceleration. The second step is actually find the final speed. And I will go ahead and I'll use the one that seems to be the most pertinent, since I don't care about time, would be v final squared v initial squared equals 2a delta x. Okay. Well, released. So it's released. So I have some idea about the initial speed, namely that it's 0. So I have the final speed squared minus 0 equals 2 the acceleration in the x direction. So I might as well plug that expression in, g sine of theta. And now I just need to get some idea about how far it slides down the ramp. Say in this direction. Give you a second to come up with that. Good. You got it? Hopefully you see right here, I've got a triangle again, right? Of physical distances. I've got a height of h. Sorry, that's not a straight line. Let's try that again. We've got a height of h. I'm looking for the hypotenuse of the triangle, which in this case is my delta x, based on my x-axis, and I have my angle. So I can say that the height divided by my hypotenuse is equal to the sine of theta. Holy shnikes! Let's go ahead and plug that in. You see that, okay, well, if that's the case, then I can write delta x as being h over the sine of theta. Right, just using this equation. Oh, goody, goody. I see that this cancels that. In other words, the angle of the ramp doesn't matter. Cool. So I get a final speed equals 2gh. And of course, square rooting that, I get v final is equal to 2gh square rooted. Okay. And I should say the angle, the reason the angle doesn't matter is because two things. Well, essentially frictionless. So it doesn't matter if this is a really small ramp, like really, really tiny, or if it's really big, really steep. Okay? The fact that it's frictionless means that the speed at the bottom only depends on its initial starting height. Okay? So let's go ahead. Let's do another question. So now, instead of thinking about forces, so let me get rid of all of this. Get rid of that. We'll save the picture for right now. Instead of doing forces, let's do it in terms of energy. Now, let's be careful here. System. What's a good choice of system? You got it? I think probably the best choice of system here, the one that'll be the fastest through, will actually be choosing the box and Earth. Okay. Surroundings? Just the ramp. Say ramp. And I'll put FN in here. Okay. Initial state, I'll say just released. Just released. Final state, man, muscle memory, excuse me. Final state is at bottom. Okay. And we'll go at it. If I say, okay, work is equal to the change in energy of my system, and I should ask myself, okay, I've got one object in the surroundings. It applies a normal force. What is the work done by the normal force on the box? Got it? You should notice that I'll say the work is 0. I'll say work equals 0. And I'll say because the normal force, the force of the ramp on the box, is perpendicular to the displacement of the box. In other words, normal force is this way, the displacement's that way. The work done on the box will be 0. They're perpendicular to each other. So the left side of this relationship equation is 0. Now over here on the right side, I need to think about what forms of energy does my system have. Got it? Say, well, the box is moving, so I have some kinetic energy. And in addition to that, my box is located above the ground. There's a change in height that's associated in there. And the observable, or excuse me, the height is the observable for the gravitational potential energy. So I'll write this down. Now let's go ahead and substitute in our definitions for the kinetic energy of an object and the gravitational potential energy. Put 0 equals, maybe I'll break this up one more step. I'll say K final minus K naught plus UG final minus UG naught. Maybe right here, this will save us a minute. If I think about the final kinetic energy and the initial kinetic energy, I can set one of those equal to 0. The initial, good. So I can set this equal to 0. I'll put an arrow, I'll say 0 because released. Released. How about the potential energies? Which one can I set equal to 0? The final, say 0 BC at ground. So I better put my ground in here. So we'll call my ground y equals 0. So I have an expression that says 0 equals the final kinetic energy minus the initial gravitational potential energy. You go. Okay. Now let's go ahead and substitute in our definitions. Okay. We have 1/2 mv squared, and this is the final, minus mg, and my initial height is just given by h. It's all 0. Oh, goody, goody. Look at this. We have a mass that cancels out a mass. And you can see it now. If I take this GH and move it to the other side, GH, multiply by 2, I get an expression for my final speed. Or, square rooting, I get V final equals 2GH. Cool. You don't seem impressed. That's awesome, right? Instead of having to do 2 steps, so first, if you think about it, instead of having to do 2 steps, forces and then a kinematics equation, I can just do it all in one if I just look at the energy instead. It's a little bit of a time saver. Okay? Cool. Okay, let's get rid of that. Okay, let's go after another example problem here. And I've already prepped it for you, so we'll go ahead and reveal the text. 2 small masses, big M and a little m, are each a distance d above the ground. A rope connects the 2 and runs over a pulley, which is located at a height h. What is the maximum height that the small mass will reach when the large mass hits the ground? Okay. So go ahead and read that. Read it over again. And we're good. Let's go ahead and draw a picture, and this should look somewhat familiar. Boom. There we go. So I've got big mass over here. I've got a little mass, and they're both located at height d above the ground. And what we're going to do is assume that these are dropped from rest, and we're going to try to figure out how high above the ground little m will reach. You say, well, this sounds familiar, Greg. We've actually done this problem before. And so what I want to do is, instead of doing forces, we're going to do this in terms of energy. Of course, you knew that was coming already. So that's what we're going to do. We're going to do this whole thing in terms of energy. Okay. Well, to actually do this, we still need, although energy makes life really easy, we still need to actually do this in 2 steps. Okay. So step one will be, we'll say during the falling phase. We'll say falling phase. In other words, when box big M is falling. And then the second step we'll consider the, if you will, the projectile phase. In other words, when the big box has hit the ground and the little box is now just flying in the air, projectile. Okay, and from the falling phase, we'll find the final speed of the box when the big box hits the ground. And in the projectile phase, then we'll actually be able to find the max height. Okay. So that's the name of the game. Good. Well, let's get at it. So we're after step one. So the first thing that we should do is we should indicate our systems and surroundings, because from the 2 steps we'll actually change that a little bit. So here in the first step for the system, I'm going to say the boxes, rope / pulley, and I'll stick the earth in here too, and earth. So that being the case, what's in your surroundings? In other words, what objects significantly interact with the system during this process? You get nothing. Nothing. So I'll do that. Okay. Now, because we're doing energy, it's usually very important to indicate initial and final states. So I'll put initial and final here. And the initial state is just released. How about the final state? I'll say when M hits. Okay. So right when M hits the ground, that's my final state. Okay. Well, now let's go to our relationship equation for energy. We've got our work equals the change in energy of my system. Now, looking at the surroundings here, what can we say that the work should be equal to if there's nothing in my surroundings? It's 0. If there's nothing in the surroundings, there is nothing to exert a force on your system in order to transfer energy to or away from the system. So in this case, our work is 0. Just put 0. And this is where we say, hey, we've got a closed system. Closed system. In other words, the energy that the system starts with stays in the system. It goes nowhere else. Okay. Now, over on this side, so that's the interaction of the surroundings with the system. Over on this side, we need to identify what forms of energy the system has. In other words, how can the energy be stored in the system? We'll say, okay, well, we've got 2. First of all, we know that we're going to get some motion. And so we're going to see changes in kinetic energy. In addition to that, what other things change? Well, the height of the boxes change, and the observable, that's the observable for the gravitational potential energy. So we're going to have the gravitational potential energy also change. Okay? And that's pretty much it. Those are the 2 forms that we care about. You could say, well, what about frictional force? We're dealing with an ideal pulley, so we don't have to worry about any of that kind of stuff. And the pulley's in the system anyway, but we don't have to worry about objects heating up or anything like that. So this is good. This is all we need. Okay. Well, I'll take advantage of the delta. The delta means final minus initial, so let's go ahead and write that in. We'll say 0 equals the final kinetic energy minus the initial kinetic energy. It's always good to write this out every once in a while just to remind yourself. Final minus mu initial. Okay. And I'll go ahead. I'm going to move the initials to the other side. So we have the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. In other words, because we have a closed system, I'll say energy is conserved. In other words, again, the total energy of the system stays constant. Sometimes that's referred to as energy conservation. Well, we're here. We should ask ourselves, based on our initial state, what can we say about the initial kinetic energy? It's 0. This is actually 0. Scratch that out. We'll say 0 because released. All right, that kind of got garbled there. Yeah, I'll just, there, pop up. Hey, nice. Okay. So it's 0 because it's released. And that's pretty much the only one. We can't get rid of anything else so far. So let's go ahead now and substitute in our definitions. And remember, we have 2 masses now, right? We have 2 boxes, and so we have 2 gravitational potential energies. One for the big mass, one for the little mass. So we just have to be careful about that. Let's go ahead and substitute in our definitions. For initial, we have the big mass times g times d, height above the surface, and I'll call right here, I'll set that equal to that as y equals 0, plus little m g d. And that's the initial, that's the starting, equals. Well, let me ask you this. How does the final speed of the big box compare to the final speed of the little box? They should be the same. Remember, the rope is ideal. We assume it doesn't stretch. The pulley's ideal, so everything's fine there. But because of those 2 approximations, that means that if the big box is going down, the little box has to go up by the same amount. So the displacements of each of the boxes, the magnitude of the displacements are going to be the same. Those are going to happen in the same time interval. The speeds must be the same. So what we'll do is we'll write this as 1/2 little m v squared plus 1/2 big M v squared. Okay? Now we have to deal with the gravitational potential energy. And here we remember that big M is on the ground. Okay. So we don't have to worry about that. Height is 0. So the only one we have to worry about is little m times g. And now my figure's a bit poor, but again, taking advantage of the idea about that rope not stretching or anything like any funny business with the rope or the pulley. If big M goes down a distance of d, little m must have gone up a distance of d. So when big M hits the ground, little m must now be at a height of 2d. Cool. Well, now all we need to do is we need to solve. You notice we need to simplify and get the speed by itself. Well, I guess we could go at that. You notice mg2d, mgd, so, oh goody goody, at least one. This will cancel, and I'll say that. There goes the 2. And doing a little bit of algebraic manipulation, we get big M minus little m times the quantity GD. Okay. We'll put a 2 in front. Over big M plus little m. This will be equal to v squared. So pause the video. If you don't see where that came from, go ahead, pause the video for a second and say, hey, where did that come from? Or maybe not, where did that come from? Maybe I should say, oh yeah, let me make sure I've got the algebra. So we'll go ahead. I'm going to store that. We'll put it right over here. Right there. That's where we'll put it. And we're done with the first part. Oh, goody goody. So let's go ahead and get rid of all of this. There we go. We are ready for the second part. So step 2, rock and roll. Now that we have the speed at which the little box is moving when the big box hits the ground, we're now in a position where we can get we can solve the rest of the problem. So here, let's go back. Step 2 is we want to find the height. And I said, hey, let's consider a different system now. And the reason I say this is, do we really need to worry about the big box or the rope anymore? No. In fact, conceptually, we could think of this as, hey, you have a box that's launched into the air. Here's its speed. How high does it go? Right? We don't care. At this point, we don't care how it actually got up to that speed. So that's, I guess, we're talking about the initial state already. Okay, we'll say little m launched. And the final state will be little m stopped. We don't care how it got up to speed. We just know now that it has been launched. So up here, we're going to use little m and the Earth. And in our surroundings, nothing. Say nothing. You say, but wait, Greg, the rope's attached to the box. Yeah, but because big M is on the ground now, there's no tension force. The rope goes slack. There's no pulling on it. Okay? So just because there's objects around, yes, but the real question is, when we're thinking about our surroundings, really the only things that we want to put in here are the things that interact significantly with the system. Box M doesn't matter. Doesn't exert a force on the system. We don't need to worry about it. Well, we are in a position to figure this out. We go back to our handy-dandy fundamental principle, change in energy of the system. Again, we see in this case, the work done is 0. We have a closed system. And similarly to the last step, we have a change in kinetic energy plus a change in gravitational potential. Yay! The final kinetic energy plus the final potential energy equals the initial kinetic energy plus the initial potential energy. Of course, looking at my final, m stopped, that means that this goes away. This is 0 because I'll say v final equals 0. And now let's substitute in our definitions. Here we have mgh, and I'll say h is my max height. Over here, 1/2 little m v squared. Put v naught so that we don't confuse it with v final. Plus mg2d. Okay. mg2d. Boom. Oh, goody, goody. Well, we see, interestingly enough, that these masses cancel out, so we'll get rid of those. And now we're in a position to use the results of step 1. We're going to substitute that in right here for that. So we get something that says, okay, well, g times h equals 1/2. And now you see why I left it as v squared, because I knew I was going to need to square it anyway. No sense in taking the square root. So I am lazy. Let's see here. If I can actually do this. 2 times m minus m g d. That whole quantity divided by m plus m. Plus 2gd. Of course, now we see, oh, goody, goody, we can go even further. 2 cancels the 2. Swap to a different color. You have a G, and a G. And so then the last thing I'll do, since we have what we want, H. Okay. Just for simplification, I'm going to take the second term. I'll multiply it by big M plus little m. Okay. So I'm finding a common denominator here. And so at the end of the day, we have H equals, I've got M plus 2M. So that would give me 3M. I've got minus M plus 2M. So that gives me 1M. So I'll put plus M. That whole thing is multiplied by D. And then that is all divided by big M plus little m. And there is my answer, which is always interesting because, again, let's make this, so there's my answer. And I always find it interesting, and I'll note it again. This is a 3. This does not depend on gravity, the gravitational acceleration. It just depends on the masses of the boxes and the starting distance. That should hopefully make some sense now. So initially when we did it using forces, I said, hey, it doesn't depend on g. Here's the max height, all that kind of jazz. Okay. But here it should hopefully make a little bit more intuitive sense now. How much energy did you have to start off with? Well, that's dictated by the initial gravitational potential energy for the arrangement that's shown on the figure here. Okay? That's the amount of energy, and it doesn't matter what else you do. That's the fixed amount. Okay? So it does seem reasonable that your final height would also depend only on those parameters, m and d. And you say, why did g disappear? It's because g dictates how much gravitational potential energy you have in the first place. So, I mean, the initial, it's related to the initial gravitational potential energy and the final gravitational potential energy. So that would cancel out. That would disappear at some point. The other thing that I always find interesting about this is that what happens if I make this infinitely massive? If I make big M really big compared to little m, you find out, I'll say the limit, we'll come up here, we'll say the limit as m goes to infinity. It's always interesting because then you end up with something like 3 big M over d divided by big M, right? Or which is equal to 3d. So it seems odd, but you can make this box infinitely massive, and the highest that you can launch it based on the highest that you can launch little m based on this arrangement is a height of 3d. It just seems kind of weird to me. I don't know why, it just does. Anyway, you know what? That's right. Without loss of generality, we called big M the heavier mass. Okay, just making sure. In any case, so that's pretty cool. We recovered the same idea. We recovered the same equation using energy, which is always good.